In section 8.4, we talked about logarithms yesterday and just kind of introduced the idea of what they are. We're going to look into those a little bit more today and how we can simplify those, and then talk more about how they are the inverses of exponentials and then how we can graph them. As logs and exponentials are inverses, they undo each other. That's what inverses do. Logs were really kind of created to undo exponentials. That's why they exist. So if you have a log with a particular base and an exponential with that same base, those undo each other, and you just end up with whatever that exponent was. Likewise, if you have an exponential with a particular base and a log with that same base, they will undo each other, and you will just end up with whatever that extra part is. Okay? So logs and exponentials cancel each other if the bases are the same. Okay? The bases must be the same for that canceling to happen. It's kind of like multiplying by 2 and dividing by 2 undo each other. But multiplying by 2 and dividing by 5 don't undo each other. Okay? So they undo each other when the bases are the same. So in this problem, we have an exponential with a base of 10. Then we have a log. What's the base of that log? 10. No base is written there, which means this is our common log, and the common log has a base of 10. So whenever you see just the word log with no base under it, that is a base of 10. So the base of the exponential is 10, the base of the log is 10, so they undo each other, just like multiplying by 10 and dividing by 10 would undo each other, or adding 10 and subtracting 10 undo each other. Okay, so since they both have the same base, they undo or cancel each other out, and we are left with just 2 as our answer.
Wait, if there isn't a base after the log, it's 10, or it's
Yes.
the number of the...
It's 10.
Okay.
It's always 10 if there's no base written. Yep. What is the base of the log in this problem? 3. What's the base of the exponent in this problem? 9. So they are not the same. So they don't directly undo each other, because if I multiply by 3 and then divide by 9, that doesn't clear each other out, right? So then our goal is, can we make them be the same? Is there a way to write one of them so that it's the same thing as the other one? So since 9 is the bigger one, is there a way to write 9 as a 3? And since we're talking about exponentials here, we want to think about exponents. 3 squared is 9. So I'm going to take that 9 and change it into a 3 squared, because 9 is 3 squared. But now the base of the log is still 3, because we didn't do anything to that, and now the base of the exponent is also 3. So they cancel each other out, and we are left with whatever's left over, which is 2x.
Why does the log cancel that?
The log cancels the exponential. So the log and the base of 3, we can't separate the log from the base of 3. So it's that this whole log base of 3 cancels the whole base of the exponent. Our next kind of problem is to find an inverse of a function. So we briefly went over again yesterday kind of the idea of finding inverses of functions. We did this a while ago in chapter 7. So the way the book is set up, you learn inverses in chapter 7, and then this is chapter 8. So like they expect it to be in recent memory of students, but we did a whole lot of stuff in the middle of those. So it's been a little while since we've done inverses, but to find an inverse, our first step is to take the x and the y and switch them. What an inverse does is it changes the output and the input of a function. So it takes the x and the y and says x used to be what's going in, and now x is what's coming out. Then we need to get y alone again. And to get y alone again, what we're going to do is rewrite this as an exponential the way that we learned yesterday. So yesterday we learned that we can rewrite this with the base staying the same and the other stuff switching sides. So the base is 3 and that stays the same, and the other stuff switches its locations. So x and y both move from left to right, or right to left. We learned back when we talked about inverses that we shouldn't really technically call this y because we already had a y, that this is the inverse of y, and we introduced that notation back then. I wasn't really picky about it before, and I'm still not going to be really picky about it, but learning that notation is probably a good thing. I have seen it show up on standardized tests and stuff if you go to retake your ACT or something.
Ms. Chair,
Mhm.
where did the -1 come from?
That's just the notation of inverse, saying that this is related to the original equation, but it's not the same y. It's the y, the inverse of that y.
Okay.
So it looks like a -1 power, but it's not. I hate that notation because it does look like a power, and especially right now when we're talking about a lot of powers. It's a pretty bad choice of notation in my opinion. Alright, so for this one, find an inverse. First step is swap the x and y. Then we want to rewrite this as an exponential. And when we do that, the base stays the same. What is the base of ln? E. ln has a base of e. ln is our natural log. And the base of the natural log is e, always. Okay. So when we rewrite this as an exponential then, the base is e, and the other stuff switches sides. So the x goes over to the right, and the y plus 1 goes over to the left. We want to get y alone, so we're not totally done with this. What do we still need to do? Subtract 1, so we get e to the x minus 1. And then technically, since this isn't really y, we started with a different y, we should say this is the inverse of y. Questions?
So you switch sides first and you switch it back?
Yeah. Doing inverses of logs is kind of a weird process because you start by switching and then in turning it into an exponential, you're really switching again. So you're kind of switching it back and forth. Last thing we want to talk about is the graph of a log function. So back in chapter 7 where we learned about inverses, we learned that when you graph a function and its inverse, they should be reflections over the line of y equals x. So before, we've already graphed exponentials. So we've already graphed things like y equals 2 to the x. And they looked like this, right? And they had a horizontal asymptote. So the graph of a log function then, if it's the inverse of it, so something like y is equal to log base 2 of x, should be a reflection over that red line. So if I take that purple function and think about folding my paper, and like if I had done it in paint or a really heavy pen, where would it leave an imprint? And it would leave an imprint that looks like this. And instead of having a horizontal asymptote, it's going to have a vertical asymptote. Okay, so a log function is going to have a vertical asymptote instead of the exponential having the horizontal asymptote. So our characteristics say that we have this vertical asymptote. Before, with exponentials, our domain was always all reals, but our range was limited. Now that's going to be opposite. Our domain is going to be limited, but our range will be all reals because these are opposite types of functions of each other. First thing we're going to do to graph is take care of any shifting. So what is that minus 1 going to do to this graph?
To the left, right.
It's kind of tricky because it's by the x, right? But it's not grouped with the x. So it's actually going to be a downshift. If we had parentheses around there, then it would be a right shift. But since it's just next to the x and not really with the x, it's not grouped together with it, then it's going to be a downshift for us. So we're start by moving our whole graph down one spot. Then we're going to think about the equation y equals log base 1/3 of x. We want to make an xy chart, but we've been making xy charts for exponentials. So let's keep doing that. But this isn't an exponential, but we can write it that way. So to write this as an exponential, it would be 1/3 to the y equals x. The base stays the same, but the other stuff switches who it's with. So before the 1/3 was with the x, now it's with the y. So rewriting it the way that we learned yesterday. Then we're going to do something a little bit weird in making our xy chart. If I picked numbers for x, then I would have to solve for y, but you don't really know how to solve equations like this yet. So what we're going to do is pick numbers for y. We're going to use the same numbers that we did before in our charts. And we're going to plug those in. So 1/3 to the -1. What does a power of -1 do to something? Flips it, so we're going to get 3. 1/3 to the 0. What is anything to the 0 power? It's 1. Gives us the number in front, which is just 1 in this problem. 1/3 to the first is 1/3. And 1/3 squared, or 1/3 times 1/3 is 1/9. Multiplying and adding. Still wouldn't be adding. We're going to plot these now on that shifted down line. So from there, I'm going to go for x over 3 to the right, and for y down 1. So that's where that first point exists. I'm plotting off of the red line, and since we didn't have any sideways shifting, the regular x-axis. So x is 3, I'm going over 3, and y is -1, so going down 1. Then the next one, x is 1, so I go over 1, and y is 0. And then x is 1/3, so I go over 1/3 and up 1. And I can't even really do 1/9 because that's really tiny. We're going to follow a vertical asymptote on the graph. And our log graphs are always going to shoot out towards the right-hand side. Okay, they could start high and then shoot out towards the right on the bottom, or they could start low and shoot out towards the right on the top, but they're always going to shoot out towards the right and always have a vertical asymptote. So then our domain, our x values, are limited by that asymptote. We're never going to cross it, so x is always going to be to the one side of this asymptote. Is it going to be bigger or smaller? Bigger, because it's going to the right, and where is that asymptote? At 0, because it's right at the axis. So we're only getting numbers on the right-hand side of this graph, or on the right-hand side of that axis at x is 0. Our range is going to be unlimited. So these are exactly the opposite of exponentials. When we did exponentials, we had a domain of all reals, but the range, we had a restriction on y. These are exactly the opposite, okay, because they're inverses. So inverses switch the job of x and y. Let's try another one. What's the +2 going to do to this graph? Go to the left 2. Because it's in parentheses with the x, that's a side-to-side shift, and side-to-side shifts go backwards. And then we don't have any up-down shift, so that's just going to stay right there. Then we can ignore the +2. But we want to make a chart for an exponential function, so we're going to rewrite this the way we learned yesterday. The base stays the same, and the other stuff switches sides, left to right. and we're gonna make a chart. But since y is with the number, we're gonna choose y values to plug in. -1, 0, 1, and 2. Five to the -1 does what? Flips it, so 1/5. 5 to the 0, 1. 5 to the first, and 5 squared, 25, and I'm not going to be plotting that one. So we talked about before with exponentials, the bigger the base, the sharper the turns they're making. Same thing with exponentials. The bigger the base, the sharper the turn it's going to be making. So when you have a large base, like a base of 5, you're probably not going to end up plotting all your points, and that's fine. So now we're going to plot these from where those red lines meet each other. So x is 1/5, so over a tiny amount and down 1. Then x is 1, y is 0. And x is 5 and y is 1. So this one starts low and ends high, but it's still shooting out to the right. Domain is limited here because we have a vertical asymptote in this problem we're not crossing. So x, is it going to be greater or less? Greater, because they are always going to shoot out to the right. And what is it greater than? -2. And our range will be unlimited. Because it is moving forever up, it's just moving up slowly. Okay. So your homework is still from section 8.4. I want to talk about just one more quick thing in terms of the graphs. Both of ours had a base of just like a regular number. I think we did, 3 and 5. So if you needed to do a graph of, let's say, ln of x, okay, you would still take care of any shifting that happens first. Then when you go to rewrite this as an exponential, what's the base? E. For ln, our base is e, so this would be e to the y equals x. You'll make your chart, but use your calculator to make your chart, okay? Because I don't expect you to be able to do e, which is a really ugly number, to powers, okay? So when you have an ln, the base of ln is e, and when you need to make a chart for that, just use your calculator to make the chart.